Hi, and welcome to Programming Like It's 1979. Lately, I've kind of fallen down a hole with a software technology called proof assistants. So I wanted to make a very short video introducing you to them, and hopefully we'll all learn something today. In my last video, I talked a lot about process in software and about how a lot of software is created in a very slapdash way. So what's the alternative? Well, there are a few, including test-driven development, but one interesting branch of checking the validity of your software is called formal verification. Among the tools that we can use for formal verification are this class of software or programming language or tool called proof assistants. Now, proof assistants are a very specific type of tool that, depending on the details and the implementation, live sort of midway between being a programming language and a mathematical utility. They've existed for years, largely used to help mathematicians prove theorems, but lately they've sort of enjoyed a second life as a tool for formal verification of software. In some cases, you could even write your software in one of these languages and have the software carry a proof of its correctness along with it. Now, that's beyond the scope of this brief video. The proof assistants I've looked into so far are Isabelle, Coq, Agda, and Lean. While these aren't tools for the faint of heart, there are actually quite a few resources out there on the internet that the self-studier can use to kind of get a chance to use them a bit and start to understand them. Probably the most well-known of these courses is the Software Foundations series of classes out of the University of Pennsylvania. This is a series of 4 classes. They're quite deep, covering topics in all the way from logic to programming language theory and onward. Today, I'm just going to take a quick look at some of the earliest bits of Logical Foundations, the first class, as an introduction to the Coq IDE, which is available for download on the internet, and I will provide the links in the notes below. You can also, instead of using the Coq IDE, use the Emacs editor and the Proof General package. Which one you use, they're roughly equivalent. I slightly prefer the Coq IDE because it's a little more ready to use out of the box, whereas Proof General requires a little more configuration. But if you're already using Emacs, it's an option for you. Now, I do have a slight problem in presenting this material to you, which is that the creators politely ask that people not publish solutions to the exercises online, because they're used in college classes. So my usual plan of work through the problem sets on YouTube won't really fly here. I think this is a real shame, but I do want to respect their wishes. So instead of working through the problems that they give, what I've done is I've picked some of the examples in the class where they've already given the answers. I've taken the answers out, and we'll work through those together. And really, I've just picked 2 or 3 so we could understand some of the very basics of Coq, some of the proof tactics that you'll be using to do some of the more elementary activities in it. The rest, dear viewer, is left as an exercise for you. So the Logical Foundations class is presented in this kind of literate programming style where the lecture notes are inside the Coq file that you're going to step through. So we can do that by holding down in Windows the Control key. On Mac, I think it's a slightly different modifier, and the down arrow. And what we just did by doing that was we stepped past all of this introductory material. Presumably you would have read it all, and gone to the first kind of statement here. And you could see the first thing it's doing is defining this inductive type of days, Monday through Sunday. And over here, right above my head, you can see we get some messages telling us those were defined. And then we can define some functions. So here we're defining a function next weekday that takes a day as an argument and returns a day. So this is kind of an enumerated type, a sum type as it were. And we have some code here saying if we ask for the next weekday of Monday, return Tuesday. If we ask for the next weekday of Tuesday, return Wednesday, etc. Lots of explanation of the programming language here. And here we see a compute statement. This is saying what's the next weekday after Friday. And over here in the status, we see Monday. So we're not going to go into all the details of Coq here. What I want to show you here is an example of the proof carrying code, right? So here we have an example. This is kind of like a test case. So now we're going to try to prove it. So let's go. We're going to declare proof. Up here in the upper right is our proof state. This is the state of the proof at the current moment in time. Next weekday, Saturday equals Tuesday. Well, the first tactic we're going to try is to simply simplify this by substituting the definitions. So we apply the simplification tactic. I'm going to hit Control down. And we can see now we've got Tuesday equals Tuesday. Well, now we have the same thing on both sides of the equal sign. So we could use the tactic of reflexivity. That means we've done it. And we could say QED, this code is now proven. Or let me rephrase that. This test case is now proven to be correct. So let's go back here. Let's change this Tuesday. Let's say the next weekday of the next weekday after Saturday is Monday. And you could see that the kind of run state of the program jumps back because we made a change. It's one nice thing about Coq IDE. We're going to read that again. And now we're going to try to run our proof again. Tuesday equals Monday. That doesn't sound great. Let's declare reflexivity. And here, the proof assistant tells us this is not proven because you're trying to use the reflexivity tactic, and the same thing is not, in fact, on both sides of the equal sign. Well, I'm going to change that back to Tuesday, and we'll continue on. So simplify and reflexivity are the two simplest tactics that you're going to be using all the time in Coq. The other thing I will say is that typing QED as you're proving things is really, really satisfying. And you're going to get to do it a lot if you do these courses. Well, let's jump ahead at this point, and let's actually do one of the examples that I had kind of picked here. So we're going to jump right to here. And I think I can do Control right arrow to get all the way over here. Right, come down here. A proof that we're trying to prove. It's a simple example. We want to say that for all natural numbers n and m, which are of course abstract or undefined, if n equals m, then n plus n is the same as m plus m. So a proof starts with the word proof and a period. And now we need to decide what we're going to do. Well, the first thing in most of the proofs that I've done so far, the first step is usually to introduce your quantified variables into the context. So that tactic is called the intros tactic, or intro. And we're going to introduce n and m. Okay, and let's step forward. So now, what do we want to prove here? Well, we have an implication arrow. And if you recall from our adventures with the incredible proof machine, the implication arrow is all about hypothesis. If this, then that. So let's also introduce a hypothesis. We'll say intros H. And now that it's above the line, we can use it in proving this. So what are we going to do? Well, first thing we can do, we can flail. It's sometimes a fun thing to do to flail at these, and just a good way to learn what the tactics do. Can we simplify it? Use reflexivity? Well, certainly not. It's not the same on both sides. Let's try it anyway. And we get told we can't unify these two things, which is what we'd expect. Okay. So what we can do is we have this hypothesis that n equals m, so that the thing below the line using that hypothesis. So we're going to use the rewrite tactic. And you can see that as we rewrite it, the n's become m's. The n's become m's. We can also rewrite it in the other direction so that the m's become n's. Either is the same for this proof, or both will have the same effect. Now that we have, now that we have the same thing on both sides of the equal sign, we can use reflexivity, at which point we can say QED. Very satisfying. Let's go forward. No more goals. And we've now proven that theorem. Well, let's look at another tactic. Let's go and look at binary and commutative, right? Remove the answer. And again, I just want to be clear for anyone out there who's getting angry watching this. These are not the exercises that you're asked to do in the class. These are the exercises for which they give you the answers. And I've just removed the answers temporarily from these files so that I can give you an idea of the flavor of the language. All right, so to prove the commutativity of and, well, let's go back and look at the definition of and, right? And b, up here. Here's the definition. Given two variables, b1 and b2, both Booleans, which are defined as true or false, some types. b1 is true, then return b2, otherwise return false. Okay, let's get back to our proof. So in order to do this proof, we are going to use what in Cork is called Destruct, the Destruct tactic, which is awfully ominous sounding, but it's short for destructure, and it's basically a way of saying case analysis. We're going to cover each case. So in this case, let's introduce our B and C. Over here, up here in the upper right, is the state of our proof. Right now we've done nothing, and we are going to introduce B and C. Those move above the line. And we want to destructure, we want to do case analysis on B. And you can name these things. I think in their example, they propose giving it the name EB. I found it seems to pick pretty reasonable names for these things. Let's see. Okay, you do actually get that little EB above the line, so that is helpful. So let's use it. Okay, so now that we are destructuring, we have to do cases, right? So we have to put in basically a dash on each line for E, and the dash indicates that that's the next case you're going to do. So the first case we're going to get to here is where we've got true and C equals C and true. Well, we're trying to prove commutativity, so we can't actually unify these yet because they're in opposite order and we don't know what C is. So we're going to have to go further, and we're going to have to do case analysis on C here. So we can do destruct C, right? Okay, and now we're going to go in. We'll indent a little more to make it easy. We'll use a different bullet this time, a plus. Okay, and now we're seeing true and true equals true and true. Well, that is reflexive. So we can just say that. That handles that. Then we add our next case, which is going to be true and false and true. Now, why can I unify these? Will reflexivity work? Yes, because these are not variables at this point. These are actual values, and actual values can just be computed. And in fact, if we simplify them, we could see it simplifies to false equals false. We don't need to simplify. Reflexivity will simplify for us, but it's nice to kind of get that visible when you're there. Okay, so now we've handled both cases of the case where B is true and both cases of C being true and false. So now we're looking at the B as is false case. And we just are, this is trivial enough that you can probably see it. We're going to do the same thing again. And in fact, I'm so confident that I'm just going to do this. I think that should do it. Let's take a look. False and C, well, that's not enough, so we destructure on C. That simplifies to false, which is true. No more goals, QED. And that is the destruct tactic. Let's look at one more. I'm going to load a different file here, actually. I've jumped ahead here to the induction chapter, and we're looking at a proof where we want to prove that for any number n, if we add 0 to it, it will still be n, no matter what that number is. Pretty simple theorem, should be easy to prove, and we could prove it using induction. So let's type proof. Let's introduce n. Can you say intro? I think you could just say intro. Yes, you can. Great. And then we're going to do induction on n. There's some really ugly syntax that they introduce here if you're doing this by the book. And I'm going to skip that syntax because I don't like it. All right, so now this feels like case analysis. And in fact, it is. There are two cases that we're going to be looking at. The first case is when n equals 0. And the second case is when n equals n plus 1, or in this case, successor of n in their language. So this first case, 0 plus 0 equals 0. Well, that simplifies to just 0. I guess I should close the comment. That would probably help. And that's proved by reflexivity. So yes, 0 plus 0 is equal to 0. We've proven that. Well, now we get to this next one, which is essentially saying S of n is successor of n, or n plus 1 plus 0 equals successor of n. But again, we don't really know what n is here. So how can we prove that? Well, if we simplify that, and if we look above the line, we see IHN, our inductive hypothesis, is that n plus 0 is n. So we can rewrite using that inductive hypothesis. And now we have n plus 1 equals n plus 1, which is reflexive, and that should prove our theorem. So there's so much more in this class, and I am very conscious that I'm kind of giving you, baby's first theorems here, and I can't really go into the meat of the class. I'm certainly not qualified to teach this class. I would feel like I was qualified to work the problems with you, but they've asked us not to do that, so I'm not going to do it. So instead, what I will say is that if the idea of learning a lot about kind of the foundations of logic, which are, after all, the foundations of software, interests you, you should check out the Software Foundations class. Now, the other idea I've had is that there's a class that is similar to this called Programming Language Foundations in AGDA. The environment to do that class is a little less easy to explain, easy to show off. If that is something that interests you, if you'd like to see me work through Programming Language Foundations in AGDA, where they have not asked people not to do those exercises online, that's something I would consider. Anyway, I wanted to just show this to you because I think it's nifty, and I figure if I think it's nifty, maybe one of you out there thinks it's nifty also. This has been Programming Like It's 1979. Thanks for watching.